Okay, so hopefully this is differential equations. Part 1. Okay, and my name is Philip Maini, and these lectures obviously Monday at this time and then Tuesday at 12 o'clock. So there'll be 4 problem sheets. They're already on the web. And when we've covered stuff within the problem sheets, I'll tell you which questions you can do. In fact, you should already be able to do the first 2 questions on the problem sheet number 1, because they are revision questions on things to do with convergence and series. And those are things we will be looking at later on in today's lecture and also tomorrow's lecture, and I'll just assume that you know all that stuff. Now, you've probably already seen on the web the synopsis of this course, and I'll go into that in a little bit of detail later on. There are also lecture notes, and I've uploaded the lecture notes of Professor Janet Dyson. And what I will do is cover the same material that's covered in those notes on the web, but I won't be using those notes. So I'll be giving a sort of complementary view of the subject. So don't be expecting to look at her lecture notes and see word for word what I've written in these lectures. We'll be covering the same material, but not necessarily in exactly the same way, but roughly speaking in the same way. When I'm giving the lecture, I'll also be expecting that you will not only be writing down what I write on the board, but also be making your own notes about various things. And what I will try and do in the lecture is to focus on what are the really important bits and why we do what we do. Okay? So this lecture course will look at ordinary differential equations in the first part, and then the second part look at partial differential equations. And what this course is trying to do is 2 things. First of all, for those of you who are interested more in sort of applied analysis and the pure side of things, to give you ideas of how you go about proving existence, uniqueness, etc., etc. For those of you who are more of an applied view, who want to solve differential equations, see what the solutions look like, it will give you methods of how you actually get the solution. So those of you who want to go on and do the more applied courses, that will relate to the sort of things that you're doing, will be doing later on. Those of you who want to do a bit more of the pure, this will give you an insight into that. And of course, the 2 things match up, because in the applied, when we come up with quick and dirty ways of getting a solution, we know that from the pure mathematics point of view, a solution exists to the problem's well posed, etc., so that we know that what we're doing is based on fundamental, rigorous mathematics. So we try and cover those 2 things. Okay? So if you can't hear me, or if you can't read the writing, then do let me know. Okay? So we'll start off, as I mentioned, the first part will be ordinary differential equations. So part 1, ordinary differential equations, and of course you've seen ordinary differential equations before. So some of this will be revision for you, but some of it will be new. So of course, we call these ODEs. And the first part will be ODEs in general, and then Picard's theorem. So Picard's theorem is a theorem that will tell us under what conditions a solution to an ODE exists and is unique. But before we do that, we have to ask the question, what is an ODE? and you all know this, but let's write it down. So an ODE is an equation for y of x, a function of x, of the form so some function g of x, y, y dashed, y double dashed, up to, say, yn equals 0, where the dashes mean derivative. So y to the r means dry by dx to the r, and y is the dependent variable, I should say. And x is the independent variable. So that means you can choose x, whatever you want it to be, and then y is y of x. It's given. Okay? So here, of course, this only makes sense if these derivatives exist. So we're making the assumption here that you can actually differentiate this function, and you can differentiate it up to n times. Okay? So if we can rewrite this as dny by dx to the n equals some f of x, y, y dashed, y to the n minus 1. So in other words, if we can get out the nth derivative and write it in terms of all the other functions and derivative, then the order of the ODE is n. That's the order of the highest derivative. And this should be all stuff that you've heard before. Okay? And so a question, or questions that we would have with our nth order ODE be, does it have a solution? And is the solution unique? And probably up until now, the examples you've looked at have been well-behaved ODEs in which you just find a solution and then you say, well, that's a solution. So you're sort of assuming that a solution exists and you're assuming that it's unique. So what we're going to do here is we're going to ask, well, how do you know that? Right? So obviously in mathematics, always a good idea is to start with the simplest problem. So the simplest problem be a first order ODE. So we start with simply y dashed of x equals f of x y dashed. And as time goes on, I will get sloppy with the notation and leave out these x's. But we keep in mind these are always functions of x. And you should know that you need an initial condition, typically. So that's 1.1. And this is called an initial value problem. Because you're given an initial value. So we just call that IVP. Now, as I mentioned, probably the types of ODEs you've looked at until now. You've just found the solution and you've got on with it, and that's that. But here are now some warning examples where ODEs are not the kind, gentle creatures you thought they were. So, warning examples. So here's an ODE, dy by dx equals 3y to the 2/3, and initial condition y of 0 equals 0. So that's an initial value problem. So let's solve this. So solve it by separating the variables. So I'll just sketch the proof of this. I'll leave you to do it properly. Okay, just separate the variables, integrate, and you end up getting, leave you to convince yourselves that you get this, where a is a constant, and that'll give us y equals x plus a cubed. And then the initial condition y of 0 equals 0 implies a is 0, and therefore y equals x cubed is a solution. You should always check that you haven't made a mistake anywhere. If y is x cubed, then dy by dx is 3x squared. And is 3x squared the same as 3y to the 2/3? Well, yes. Y to the 2/3 is x squared multiplied by 3y squared. Does it satisfy the initial condition? Yes, y of naught is naught. So there's a solution to the problem. And notice I've said there is a solution. I've not said there is the solution. Because if you were really lazy, you would just look at that thing up there, and you would say, well, if y was 0, dy by dx would be 0. So 0 equals 0, and y of 0 is 0. So you could just say y equals 0 is a solution. So there's more than one solution. In fact, there are an infinite number of solutions, because if we took a less than or equal to 0, less than or equal to b, and if we define y to be x minus a cubed for x less than a, to be 0 lying in between, and to be x minus b cubed for x greater than b, that would also be a solution. So let's just check. Well, again, if you differentiate this, you get dy by dx is 3x minus a to the 2/3, so that's fine, satisfies the equation. Y equals 0 satisfies the equation. This satisfies the ODE, and y of 0 is 0. So that satisfies it. Okay? Now, does a derivative exist for all values of x? Well, yes, because this is sufficiently smooth that if you look at the derivative of this, if you look at this at a, and look at this at a, the derivative is 0. So this is a continuous function with continuous first derivative. So you can talk about dy by dx. But now a and b within these conditions can be anything. So you've got an infinite number of solutions. Okay? So infinite number of solutions. Right, so that looked like a very nice ODE, turned out to be pretty nasty. Now let's look at another problem. dy by dx equals y squared, y of 0 equals 1. Exercise, show that this gives you y equals 1 over 1 minus x. Again, do separating the variables and derive it, okay? And then just check it. Do dy by dx, and then make sure it's y squared, y of 0 equals 1. And then as x goes to 1, y will go to infinity. Therefore, solution only exists for x less than 1. So if you were to try to solve this problem on a domain that included x equals 1, it doesn't have any solution. So here's an example where there's no solution, and here's an example where there are an infinite number of solutions. So going back to our question, does it have a solution? Answer no for this one. Is it unique? Answer no for this one. And you can see, crucially, it depends on these functions here, the f and the initial value have been chosen to make sure that these don't behave properly. So that's where we need to figure out then what was so special about these right-hand sides and the initial value so that things didn't work the way we would like them to work. So basically, the sort of thing that we want to do is we seek a solution. So first of all, what that tells you is there's a problem here that needs to be solved. Just because you got an ODE, an initial value problem, doesn't mean you can write down a solution. It may not exist, and there may be more than one solution. Okay, so 1.1, way up there, the initial value problem. So we seek a solution in the region, in some region, right? Because notice here, if we were to say, let me take the region to be x less than 1, then this would have a solution. So the important thing is not only what is this f and what is this, is also in which region do you want the solution to be. So we seek a solution to 1.1 in the region R, standing for region, xy, such that, so A, we've got y of A equals B. And so basically what we're saying is that if we consider A and B in the plane, and we're told that y at A is B, then is there a region around there where we have a solution? So let's just draw this. And so here's A, here's B, and then this region, be roughly speaking, something like this, where this is 2k, and this is 2h, right? That's that region. Should say h and k are obviously bigger than 0. So the sort of thing we're saying is, if we know the solution at this point here, and then dy by dx equals f something, So we know the derivative. Can we find a solution for these values of x? And it lies in this region. Okay? So we make some assumptions. So assumption 1 we will make we will assume that f of x, y is continuous in R. Okay? So let's integrate 1.1. So integrate it from a to x. Okay, because we've got it at a, and we want to find it at some point x. So using t as a dummy variable, I mean, if we integrating from a to x, now use a dummy variable, dy by dt, that's going to give us y of x minus y of a. And then on this side, we're going to get from a to x f. So t is just the dummy variable, dt. And that gives us that. And therefore, we can say y of x equals y of a, which is b, plus the integral from a to x f of t y of t dt, 1.4. So now we've got an equation for y, which is fantastic, except for the fact that it involves y on this side. Now this might look to you more complicated than what we started off with, but this is the key thing. And what we're going to show is we're going to ask the question, under what conditions can we find a solution to this? And those conditions, we will see, make conditions on f and the conditions of where x must lie. So we're going to try and do this by 1.3, Picard's method of successive approximation. Okay, so before we do that, we have a bit of a break. The equal to sign here, which we all use, do you know when that was invented? Yep.
When it was invented?
Mm-hmm.
It's somewhere in the 16th or 17th century.
That's right. If you go to lecture room 5, L5, and look at the far wall, there's a framed copy of the manuscript which the first time apparently someone used the equal to sign. And it was somebody from All Souls, and it was in the early 1500s. And up until then, what you would write is equal to. So you would say y of x is equal to. Right. Why wouldn't you? And then this person from All Souls said, it's really tedious writing down is equal to. So I'm going to write two parallel lines, because nothing can be more equal than two parallel lines. So just think about this. When you're walking around Oxford, you're walking past colleges, or you might even be living in colleges that are older than the equal to sign. Isn't that amazing? Now, personally, I wish he'd used a smiley face. So y of x, smiley face, b plus integral from a to x. And then I got to thinking, what would not equals to be? Maybe grumpy face. But then what about greater than or equal to? So should equals to be sort of neutral face, and then greater than be smiley face, less than be grumpy face. But then what would not equal to be? Very confused face. Okay? Now, important thing, I am not on the examining committee, so I will not be examining this paper, so do not put smiley face in the exam, right? Because the marker will not know our code. So don't use smiley face. Okay? So use equal. Right. So now we had that little break and a bit of a laugh. Now we can get back to Picard's method of successive approximation. So what he said is, let's start with the guess y of 0 equals b. Good guess. And then we'll iterate up. So what we'll do is we'll put b into here, and that'll get us the next guess, y1. And then we'll put that into here, and that'll get us y2. And we'll keep on and on going, and hopefully it will converge. Or under what conditions on f will it converge? So basically, y at n plus 1 of x will be b plus the integral from a to x, f of t, y of t dt, and that is 1.5, equation 1.5. And now you see why I mentioned at the beginning of the lectures that we were going to be talking about convergence, and that you need to know stuff about convergence from last year. So does this converge? And you should know that if you want to figure out how something's converging, you've got y1, y2, y3, etc. You look at the difference between them, and you ask the question, as you move along the sequence, does that get smaller? That's one of the important points that needs to happen. So we need to find the differences between, sorry, made a mistake, that should be yn. We need to find what's the difference between y at n plus 1 and y at n. So we define E0 to be b, and then En plus 1 of x to be yn plus 1 of x minus yn of x. So that is 1.6. And then we note that yn of x is just the sum of the e's, going k equals 0 to n ek of x, 1.7. And so now we look at these e's, and we ask the question about, are these e's getting smaller as n gets larger? And you should know certain theorems from last year, that if we can bound the ENs by something, then using Weierstrass M test, various things like that, we can say that the series converges. And if you don't remember that, then that's the first thing you should be doing today, is look back on your notes, and by trying to answer questions 1 and 2 on problem sheet 1, those will show you what you need to know. So look those up. Okay? Right, so what we will do is we will write an equation for En plus 1. Well, En plus 1 is y of n plus 1 minus y of n. So the b's will cancel. And so what we will have is integral from a to x, f of t yn of t minus f of t yn minus 1 of t dt. And we need to look at the modulus. So the modulus en plus 1 of x is then less than or equal to integral from a to x, the modulus f of t yn of t minus f of t yn minus 1 of t dt. And that's 1.8. And now, crucially, we need, wouldn't it be really nice? You see, if we want to really do something with this, it would be nice if we could get an e out of here, an en. So it would be nice if we could relate f of t yn minus f of t and yn minus 1 to something to do with yn and yn minus 1, because that would give us an e. In particular, it'd be really nice if we could say this thing here was bounded by something times yn minus 1. And that's exactly what the next condition is. It's called Lipschitz condition. So a function f of xy continuous on a rectangle R, it's the rectangle we've been talking about, satisfies a Lipschitz condition with constant L. We'll see what that means in a minute. With constant L, if there exists a real positive L such that f of x minus u, f of x comma u minus f of x comma v is less than or equal to L u minus v for x u x v, an element of the rectangle. So take any two elements of the rectangle and any 2 points inside that rectangle, and if this is satisfied, then, so this is true for all points on the rectangle, then it's called Lipschitz. Okay? So just to relate that to something that you've already done. So suppose f is differentiable with respect to y, and suppose it's the partial derivative is bounded above by k. Suppose that's true for all x and y in the region. Then you should know from last year, the mean value theorem tells you that for 2 points, xu, xv in R, that's going to be equal to the partial derivative at some w, u minus v. So the mean value theorem is written without those moduli signs, but we can just put those moduli signs in, where w is some intermediate value. Okay, so it's like intermediate value theorem. 1.10. And then if our f is bounded, or the partial derivative is bounded by k, then that would be less than or equal to k. And that's, so k would be our Lipschitz constant L. So what that's telling us is that if f is differentiable in y and the derivative is bounded above, then it's Lipschitz. F is Lipschitz. Okay? But notice, as another example, f of y equals mod y. I'll leave you as an exercise to show that this is Lipschitz continuous. Okay, it's continuous, and it satisfies Lipschitz condition. In fact, L is just 1 for that, okay? F of x u minus f of x v, modulus sign of that would be just the modulus of u minus v, so L is 1. But this is not differentiable. At y equals 0. Because the limit as you go from positive y is 1, as you go from negative y is minus 1. Okay? So this isn't a necessary condition. Okay? So that is just as a little digression of how of thinking about how you might go about finding the L, or showing that something is Lipschitz continuous. Okay? Right, so now we're going to use the Lipschitz condition in order to prove the theorem of, does the initial value problem have a solution, and is it unique? And that's Picard's theorem. Okay, so theorem 1.1, Picard's theorem, sometimes called Picard's existence theorem. So the initial value problem, 1.1, let's just write it down again. So I'll go between using dashed and d by dx. It's all the same thing. With y of a equals b has a solution in the rectangle we've been talking about all along, in the rectangle R, which is defined as, well, again, we're just writing down stuff we've already written down. X minus a less than or equal to h, y minus b less than or equal to k, provided P1, P for Picard, A, F is continuous in R with bound M, that means mod f of xy is less than or equal to m for all xy in R, and B, M h is less than or equal to k. And we'll have to figure out why that is the case. P2, F satisfies a Lipschitz condition in R. You can sort of start getting a vague idea of why this might work, because if this holds, this here holds, then when you go up to En plus 1, then that will become the less than or equal to the integral from a to x of L times En. So now you can see, you can start then getting an idea of a recurrence relation for En. And then you can see if you can get what En is, and then if you get what En is, you get Yn. And then you figure out, well, does this converge? Okay. And that's where you need to use things like the Weierstrass-M test and stuff like that. Okay. But let's do that properly. But before we do that, one more thing about this. If this all holds, as a bonus, the solution is unique. So remember those problems that we had at the beginning of the lecture, the two problems we showed where either a solution didn't exist or a solution was not unique. If you go back and look at those problems now, what you will see is that they didn't satisfy Lipschitz condition. Okay? So that'll be an exercise for you to do, is to show that those problems that didn't work don't contradict this. Okay? Right, so to do the proof of this, well, first of all, we need to show, if we're going to show that F satisfies Lipschitz condition in R, and if we're going to end up using this, then we sort of need to make sure that the y's are in R. Because if one of these yns doesn't lie in R, then we don't have any idea about F. We just have conditions on F if F is of xy, where x and y lie in R. Now we can make x lie in R. We can just make mod x minus a be less than h. But then y is given by that integral. How do we know that lies in R? If it doesn't lie in R, we're stuffed. So the first thing to do, we need to hopefully yn will lie in R. So each yn of x is continuous, and its graph, which basically means its values, that's what this graph means, lies inside R. And to know what does that mean precisely, it means that if mod of x minus a is less than or equal to h, then yn of x is an element of R. Or another way of putting that, that means yn minus b modulus of that is less than or equal to k. right? So is it continuous? Well, that's obvious. Why is that obvious? Well, how do we define the iterates? That's continuous. If we assume yn is continuous, then yn plus 1 is continuous because f is continuous. So if we assume that yn is continuous and lies in R, then that's continuous. Integrate, that's continuous. So if yn is continuous and lies in R, then yn plus 1 is continuous. But y0 is continuous, so yn plus 1 is continuous. So that's easy. And now, does it lie in R? Well, we need to show this. We need to show that's less than or equal to h. Well, that's less than or equal to the integral from a to x by its definition. Okay? Take that to that side. And we've got that. And now assume that yn is an R. So assume that holds. Then that means f is on a function that lies in R. And therefore is bounded by m. So this is bounded by m. So I've got integral from a to x m, which is just m. And I can put mod x minus a, because a might be less than x. But x minus a, if we're in R, x minus a is less than or equal to h. Less than or equal to mh. Now this is really annoying, because we wanted yn plus 1 minus b to be less than or equal to k. And we've ended up getting yn plus 1 minus b is less than or equal to m times h. So if only m times h was less than or equal to k, we'd be all right. Oh, it is less than or equal to k. Fantastic. So what we've shown then is that if yn lies in R, mean has got yn minus b less than or equal to k, then yn plus 1 has got yn plus 1 minus b is less than or equal to k. So now let's look at y0 for the induction. y0 minus b, well, y0 is b, is 0, which is less than or equal to k. So by induction, result true for all n. Okay, so what we've done then is we've shown that if these conditions are satisfied, then the iterates of y lie inside the y minus b is less than or equal to k. And what that means is now we can go back to the en, and now we can look at these things and we can say these lie within R, and therefore we can use this. And that will enable us to simplify this and get the convergence result, right? So what you need to do for tomorrow is to make sure that you know the Weierstrass-M test, because that's what we'll be using tomorrow. So go back and revise that. So what we'll do tomorrow is we'll show that we get the convergence, and then that will prove the theorem. Okay?